Good morning. I am Sourav Mishra, a PhD student in the Aerospace Engineering Department of the Indian Institute of Science, Bangalore. I'm working in the Artificial Intelligence and Robotics Lab headed by Dr. Suresh Sundaram. At AIRL, we look into the current advances in artificial intelligence and robotics, and I am also a part of the Wipro IISc Research and Innovation Initiative team that develops algorithms for autonomous vehicles and looks into explainable AI research as well. In this work, we present a novel method for knowledge distillation. Before we proceed further, I would like to thank IEEE and IJCNN 2021 for giving us the opportunity to present our work. With the advances in deep learning, neural networks have grown deeper than ever. Although deeper networks can learn rich features from huge amount of data, these are not suitable from a deployment point of view where one faces memory and time constraints. So this is where knowledge distillation comes to the rescue. These methods aim to transfer the generalization power from big models to smaller ones without compromising on performance. An example is shown in the image on the bottom left. This was proposed by Hinton in his paper on distilling the knowledge in a neural network. The student receives supervision from the teacher model in the form of soft targets in addition to the one hot labels. The soft targets capture the correlations between the confidences assigned to incorrect classes. This is called as dark knowledge and it has been observed to improve generalization. For example, a cat is more similar to a dog than a vehicle. Soft targets also smoothen out the gradients and help in faster convergence. Over the years, distillation methods have encompassed to include different types of supervision from the teacher models, like those involving the intermediate layers. One such method is the activation transfer proposed in the paper Knowledge Transfer via Distillation of Activation Boundaries Formed by the Hidden Neurons by Hio et al. In 2019. It was observed that transferring the activations of the hidden neurons rather than the response magnitudes resulted in better generalization. Distillation has also been used to transfer desirable properties of smaller models such as robustness to overfitting to bigger ones. The requirement of large data to train bigger models is addressed by augmenting the existing samples with perturbed ones. The perturbations are computed by ascending the gradient of the loss function. This method is presented in the paper Few Short Learning of Neural Networks from Scratch by Pseudo Example Optimization. However, the current methods fail to appreciate the fact that not all the samples in the training data contribute equally to the knowledge of the teacher's model. Samples contain varying amount of information and it would make sense to treat them accordingly to improve the distillation performance. The existing methods either use all of the training data or end up creating more synthetic data than what is required. We propose a mechanism to address this issue of inefficient data usage. In this context, the self-regulated learning of RBFs provides a useful case study. Learning takes place in a metacognitive framework wherein the metacognitive element decides the action to be taken for each sample depending on the performance of the model on it, which is also known as the monitor signal. So we adapt this self-regulated learning procedure to train the teacher model. Following the training, the significance values of each sample in the training set is determined. Unlike conventional distillation, now there are two types of supervising signals, the significance values and the soft targets. Significance values will be explained shortly, and accordingly, we propose three types of distillation methods. One is the significance based distillation. This method is otherwise similar to the conventional approach, except that the loss function is weighted by the significance values of the samples. The second is the regulated distillation, where only the soft targets from the teacher model are used, whereas the student uses them and learns in the self-regulated framework that we propose. And finally, the hybrid distillation, where the student uses the significance-based loss function as well as it learns through the self-regulated learning mechanism. These methods are summarized in figure 7 and the self-regulated learning mechanism which we propose is shown in figure 6. Here, the monitor signal consists of two parts, the model's prediction, y hat, and the difference between the maximum and second maximum predicted probabilities if the prediction is correct, that is delta. The action to be taken is updating the parameters of the model on the current sample, and the parameters are updated if either the model's prediction is incorrect or if the difference delta is less than a threshold eta. The threshold is an increasing function of the number of epochs, and it reflects the fact that the model's confidence in the correct prediction increases with the number of training epochs. So the difference delta must also increase with the number of epochs. The function chosen for this purpose is shown in the figure 6, and the parameter alpha controls the rate at which the threshold grows. If we set alpha is equals to infinity, we get the conventional training method where each sample participates equally. Using this type of threshold allows us to filter out samples on which the model gets confident quickly. These samples are the so-called easy samples. Now we come to the computation of the significance values. For this purpose, the participation of each sample in the self-regulated learning mechanism is noted, and then it is min-max normalized in a class-wise manner to give the significance values. For our experiments, we use the MNIST, FashionMNIST, and CFAR10 datasets, and LeanNet 5 and AlexNet models as the teacher models, and their half variants as the student models. And we compare our methods performances with those methods that use only the output probabilities of the teacher model to supervise the student model. So now coming to the results. So from this table, we observe that the self-regulated training achieves the same level of generalization as the conventional training method. Um, in the case of FashionMNIST, the results are always better with the self-regulated training. Um, Next, we visualize the sample significance histograms, and that tells how many samples actually mattered for the learning of the teacher model. And from the large bars in the 0 to 0.25 range, we conclude that a large portion of the dataset is insignificant towards learning. And for the FashionMNIST dataset, classes 0 to 4 and 6 have similar shapes of the significance histograms, and these are a bit flatter than the other classes, indicating the presence of more significant samples. The reason is that these classes correspond to t-shirt, coat, pullover, and shirt classes. Since these items are similar, the model needs to see them more often to be able to distinguish them. In table 3, we compare the performance of the proposed distillation methods to other methods in the literature, and we observe that our methods achieve as good performance as the others. And the performance of hybrid distillation becomes better for more realistic datasets like CIFAR10. Otherwise, it is slightly lower. It would seem that self-regulated learning in the student model has an opposing effect to the significance values computed during teachers' training. This means that the student identifies different samples as significant compared to the teacher during its self-regulated training. And this is expected because these models have different architectures. Finally, we evaluate the sample efficiency of our methods. Sample efficiency is obtained by summing up the participations of all the samples and dividing it with the number of points in the data set times the number of epochs. So this is also equal to the ratio of the total samples utilized in the proposed distillation to the total samples utilized in the conventional distillation. And it turns out that our proposed methods are highly efficient in terms of data utilization, and as less as 0.7% of the samples are used for the MNIST dataset to achieve similar performance as other state-of-the-art methods. Sample efficiency is not evaluated for significance-based distillation because it is merely a weighted variant of the conventional distillation. As Future directions, we would like to investigate the following. First would be extending this approach to generative models for data-free knowledge distillation. Second, we would like to identify the significant samples in an end-to-end manner without waiting for the teacher's training to end. Um, we would also like to come up with a stopping criteria for self-regulated training. Currently, we set the number of epochs to a constant value. uh, this will coming up with an appropriate stopping criteria will help us to note the convergence characteristics of the proposed algorithm. And finally, we would also like to see what is the minimum number of samples required to represent the knowledge level of the model to a given extent. So thank you very much. And this is the end of our presentation.